Okay, welcome to electrocardiography, sometimes referred to as ECG or EKG. Today we'll spend a little bit of time looking at the function of the heart, specifically the electrical system, and we'll conclude with some analysis of Biopac data. I want to begin our journey inside the heart as we talk about blood flow. And it's from the right side of the heart that receives blood returning from the body. That blood, pictured in blue, is deoxygenated, meaning it's made its way to the systemic circuit where oxygen has been extracted by the tissues, by the brain, the organs, the muscles, and returned to the heart as deoxygenated blood. Now that deoxygenated blood first arrives in the right atrium, passes through the tricuspid valve into the right ventricle, and is pumped out to the lungs. This blood pumped out to the lungs, while deoxygenated, is soon going to bind with oxygen, and that oxygenated blood is going to then be returned to the heart. It's the left side, you see, that receives oxygenated blood from the lungs and then pumps that blood out to the systemic circulation. To our brain, working muscles, areas that need oxygen receive that blood from the left side. Let's take a closer look at the blood flow through the heart. Let's start here with blood returning from the upper and lower body. Here we have pictured the inferior and superior vena cava. That blood, you'll see, enters into the right atrium, and from the right atrium we pass through the tricuspid valve into the right ventricle. It's from the right ventricle that blood is going to be pumped through this pulmonary valve, sometimes referred to as a pulmonic valve. That blood makes its way into the pulmonary arteries and ultimately finds its way at the lungs. This is a good opportunity for me to pause and say, let's keep in mind the function of arteries and veins. Arteries always carry blood away from the heart. Veins always carry blood toward the heart. However, arteries can carry oxygenated or deoxygenated blood. You see here, we have pulmonary arteries moving blood away from the heart, carrying deoxygenated blood. But here we have arteries, again carrying blood away from the heart, carrying oxygenated blood. So it'd be a misnomer or incorrect to say arteries always carry oxygenated blood, because simply we know that's not true. Here we just saw pulmonary arteries carrying deoxygenated blood. It would be correct to say arteries always carry blood away from the heart. Veins always carry blood toward the heart. Okay, let's continue our discussion. Here's our pulmonary veins carrying oxygenated blood from the lungs back to the heart. That blood makes its way into the left atrium. From the left atrium, we travel through the bicuspid valve. From the bicuspid valve, making our way into the left ventricle, soon being pumped out through that aortic valve and into the systemic circuit, where this blood is going to be traveling to the rest of the body. Now it's in the rest of the body at the capillary bed where that gas exchange occurs. Now real quick, I want to point out here, as we traveled from the superior and inferior vena cava, we made our way into the right atrium, and then we first traveled through this tricuspid valve. That was right here. And some of you will recall that tricuspid valve has 3 leaflets. On our left side of the heart, as the blood moved from the left atrium into the left ventricle, we traveled through the bicuspid valve. One of the ways that I like to remember this is, I think to myself, if I'm always starting with the vena cava and making my way through the heart in the order that we just showed, I think to myself, whenever a person were to go to the store, doing a little bit of shopping, they tend to use the method of try it before you buy it. And if we think about somebody who tries it before they buy it, that tells me that the tricuspid valve comes before the bicuspid valve. So if we follow blood flow in this manner, here's the tricuspid valve, and here's the bicuspid valve. Hopefully you'll not forget that. Okay, continuing our discussion with the electrical activity, you'll understand that there are a number of different areas in the heart which generate electrical activity. But it's the SA node, or the sinoatrial node, that is the heart's pacemaker. Everybody that has a resting heart rate, typically that resting heart rate is generated by the SA node. Now in some cases we could have some pathology. We could have the heart rate being generated from areas outside that normal pathway. We could have some disruption to the function of the SA node. In that case, we may have other areas of the heart taking over. But for many of us, in a healthy sense, the SA node generates that rhythm. And you see here, we see that it tends to beat at about 100 beats per minute. Well, that would be with very minimal regulation. But we all know if we were to sit and take our resting pulse, some of you would have a resting pulse in the 60s, some of you in the 70s, some of you in the 80s. But many of us would say my resting heart rate is very rarely at 100. So why is it that if the SA node beats at 100 beats per minute, my resting heart rate is lower? In fact, it's because we have parasympathetic tone stimulating the heart, acting like a brake to slow the SA node down. And that parasympathetic activity is what slows a person's heart rate. As a person withdraws parasympathetic activity, they pull the foot off the brake, the heart gradually begins to beat faster. It's like when you're in your car at the stoplight. Light turns green, you lift your foot off of the brake. You haven't hit the gas yet, but the car starts to move forward. Parasympathetic tone operates in much the same way. As the foot is placed on the brake, the heart slows down. As the parasympathetic tone withdraws, the heart speeds up. Now, in the case where we have to participate in high-intensity exercise, where the heart rate is going to speed up more than 100 beats per minute, that'd be like applying the foot to the gas pedal, activating the sympathetic nervous system. And you'll learn a lot more about that as you go forward in human physiology. I want to take a moment to talk to you about the electrical activity in the heart. This here is the EKG. Some of you are familiar with a 12-lead EKG. In this 12-lead EKG, I want to take note of our 12 leads. Here's lead 1, lead 2, lead 3. This is called AVR, AVL, AVF. These are all limb leads. These 6 leads are called limb leads. Then you have precordial leads. These are leads that surround the heart. Here's V1, V2, V3, V4, V5, and V6. V1, V2, V3, V4, V5, V6 are precordial leads. They surround the heart and they give a different perspective of the heart. We're going to talk about that in just a moment. Down below you see our typical ECG rhythm. We have a P wave. We have this downstroke, that's our Q. This upsweep is our R wave. And then this downslope is the S. Then we have this bump here, that's the T wave. We're going to talk about all of these components and what they actually represent in just a moment. But with this EKG, or this rhythm strip, this would be over time. Do you see these little hash marks here? and these hash marks here, and these hash marks here, and these hash marks here. Each of these distances is a 3-second period of time. So this would be 3 seconds, 6 seconds, 9 seconds, and 12 seconds. Now that means what's happening over here is about 10 or 11 seconds after what happens over here. So we cannot directly compare what happens at this point in time to what happens at this point in time, because in fact it's 10 to 12 seconds later. In other words, the heart could have had a dysfunction that quickly resolved, and 5-10 seconds later we don't see that disruption. So we could have some abnormal rhythm in one area of a rhythm strip and another area of the rhythm strip that looks perfectly fine. You'll notice again that each of these leads has a little bit of a different rhythm pattern. And that's because each of the leads is looking at the heart from a different perspective. Think of it like a camera positioned all around the heart. Each camera captures a different angle. And so it's a cardiologist that can look at an EKG or a rhythm strip and identify pathology in certain areas and determine where a person may have pathology. The red line that you see here, that's to indicate everything touching the red line occurred at the same point in time. So what happened in lead 3 right here happened at the same time as what happened in lead 1 right here. Now remember, if I look over here, what happened over here occurred about 3 seconds later than what happened over here. And you'll notice that this P wave is upright, this P wave has a negative reflection, and that's simply due to the fact that lead 1 looks at the heart from a different angle than AVR. Let's look at the electrical activity with a little bit greater detail. We'll start our journey at the SA node. From the SA node, we have this electrical activity that propagates across the atria and facilitates atrial depolarization. The atria then begins to contract. As the atria contracts, blood is pumped from the right atria into the right ventricle, from the left atria into the left ventricle. Blood moves from the atria into the ventricle, and as the blood is moving, we see the electrical activity make its way to the AV node, and there's a little pause of the electrical activity at the AV node and the bundle of His. Now in that AV node and bundle of His, where the electrical activity pauses, that's incredibly important in terms of physiology. See, electrical activity would move very, very fast. Blood flow doesn't move as fast as the electrical impulse. And so, as the SA node distributes the electrical activity across the atria contract and move blood into the ventricles. If we didn't have a pause here, the electrical activity would already be down at the ventricles, and as the atria were contracting, the ventricles would be contracting at the same time, and we'd have no net movement of blood. But instead, because of that pause, the SA node is able to contract, the atria are able to contract, moving blood into the ventricles. The electrical activity is paused. Now the blood is housed within the ventricles. The electrical activity can continue, propagating down the bundle branches on the right and left side. And then these little projections coming off the bundle branches, these are called Purkinje fibers. Okay, let's take a quick look at the detailed EKG. So we've talked a little bit about the EKG and the rhythm. Here's our P wave. And as we saw on the previous screen, here's our Q, R, S. Then we have this bump on the back end, that's our T wave. Now each of those represents a physical change in the electrical impulse. For instance, the SA node begins propagating the electrical activity across the atria. Here we see our internodal atrial conduction pathways. It's the pathways where the electrical impulse is propagating across the tissue of the atria. That propagation facilitates atrial contraction. Another way to refer to that is atrial depolarization. The atria contracts and moves blood from the atria into the ventricles. It's here that at the AV node and bundle of His, we have the electrical activity pause. This here is called our isoelectric line. There's no electrical activity along this line. And it's this pause in electrical activity that allows time for blood to move from the atria into the ventricles. Now that all the blood is in the ventricles, the electrical activity resumes as the electrical impulse continues down the bundle branches and Purkinje fibers, which facilitates contraction of the ventricle. We can also refer to that as ventricular depolarization. You'll notice that atrial depolarization is a lot smaller than ventricular depolarization. You see, that's because the muscle in the ventricles is a lot larger. It generates a lot larger impulse on the EKG. After ventricular depolarization, we see a pause in the electrical activity and then a big bump here, which we refer to as ventricular repolarization. Ventricular repolarization is the resetting of the ventricular myocytes, returning back to their resting state. Atrial depolarization was atrial contraction. Ventricular depolarization was ventricular contraction. And ventricular repolarization, that's your ventricular relaxation or resetting of those myocytes. Some of you will notice, well, I don't see atrial repolarization. Well, that's correct. You don't see it on this picture because atrial depolarization occurs and very soon after atrial repolarization occurs. The problem is atrial repolarization is covered up by ventricular depolarization. You see, the atrial resetting occurs right around this time point. So we would have a little bump here. But instead, the larger mass of the ventricular muscle overshadows the atrial repolarization. So we just don't see it on this figure. But rest assured, it does happen. Now this figure is wonderful in its illustration of the propagation of the electrical activity and the generation of our PQRST waveform. Let's start here in the SA node. Here's our electrical activity. The impulse is initiated at this sinoatrial node, and we then have propagation across the atria. As this electrical activity begins to propagate across the atria, this electrical impulse generates our P wave. It's the atrial excitation that completes our P wave. So with completion of atrial excitation, we're going to have atrial contraction, moving blood from the atria into the ventricles. It's during that period of time where blood is moving from the atria into the ventricles that we have an impulse delay at the AV junction, the AV node, and the bundle of His, facilitating the movement of blood. Now soon after, that electrical activity continues down our bundle branches and these finger-like projections of the Purkinje fibers facilitating contraction, let's call it ventricular depolarization, as the muscle of the ventricle contracts. Now that's going to move blood out to the systemic circuit. Now soon after ventricular depolarization, you guessed it, we have the resetting or ventricular repolarization. So that's our basic PQRST following the electrical impulse from the SA node to the AV node, the bundle of His, down the bundle branches, and Purkinje fibers. So let's go back to this 12-lead ECG. Now I've added one thing to this 12-lead ECG. Do you notice this lead 2? It's actually duplicated. Here's another lead 2. Sometimes when you see a 12-lead ECG, remember here's 1, 2, 3, AVR, AVL, AVF, V1, V2, V3, V4, V5, V6. Sometimes with our 12-lead ECG, we have a continuous lead strip on the bottom. And it's that continuous lead strip that's on the bottom which is consistent for lead 2 for that 12-second period of time. In other words, this is the same lead 2 for all 12 seconds. I want you to look at those blue dots on the screen. Those are marking P waves. So each of those blue dots represents a new ECG complex. Now right next to the blue dot is this QRS complex, and the little bump that we see here, that's our T wave. Here's our P, QRS, and T wave. Very similar to what we've seen already. So one thing that we can do with an ECG is we can calculate the rate. Now the easiest way to calculate the rate is illustrated in this figure below. We find a QRS complex that is sitting on one of these dark lines. You notice these dark lines and then these lighter lines? So each of these dark lines is separated by 5 small boxes. So here's a dark line sitting on, or here's a QRS complex sitting on one of these dark lines. And if we count over dark lines until we find our next QRS complex, we can determine at what point the next QRS complex occurred, and therefore calculate the rate. Let's do this together. So if we have our QRS complex sitting on this dark line, if the next QRS complex occurred on this dark line, that person would have a heart rate of 300. From this dark line, if the next QRS complex happened at this dark line, we would have a rate of 150. If it happened over here, 100. Over here, 75. If it happened over here, 60. So this is telling you that this person's heart rate is somewhere between 60 and 75. In this case, it's closer to the 60, so we might estimate somewhere around perhaps 65, 68 beats per minute. Let's do this together. I want you to calculate the QRS, or find a QRS that's sitting on one of those dark lines, and I want you to calculate the heart rate. I want you to pause the video, see if you can do it. Okay, let's find one of our QRS complexes that are sitting on a dark line. Some of you might have picked this one here. Here's a dark line, and we've got a QRS complex that's sitting very close to that dark line. And if we count the number of small, or count over the dark lines, here this would be 300, 150, 100, 75. So it's somewhere between 100 and 75. And if you'll notice, it's a little bit closer to 75. So we might estimate this person's heart rate to be 80 beats per minute. Now remember I mentioned to you that we have these limb leads and these precordial leads. Here would be an example of the limb leads placed on the limbs, the right arm, left leg, left arm, right leg. But we also have these precordial leads. These are surrounding the chest. And these precordial leads are going to look at the heart from a different perspective. See, our limb leads allow us to look at the heart from a lot of different angles in more of this frontal plane, while the precordial leads allow us to look at the heart from more of a transverse plane. It's these leads that create a hexaxial system which produce pictures from different angles. And between the two different sets of the precordials and the limb leads, we can get a pretty good picture of what the heart looks like. And that's something that we're going to do in lab, is we're going to be looking at some of the limb leads and analyzing one of our rhythms to identify some of that PQRST complex. Let's take a look.
Okay, welcome. This lab is our EKG, electrocardiogram. And we're going to be looking at changes in the electrical activity under different scenarios. So we've got our hardware set up with our electrical lead set connected to channel 1. We have already prepped the participant with an electrode on the arm and an electrode on each of the feet. And we'll go ahead and complete our calibration. Now for our calibration, it recommends that we be in a resting position. We could do that in a lying down position, or in our case, we'll just do that in a seated position. We'll go ahead and click calibrate. The key here is to sit real still during that calibration process. And we have to sit real still because any movement that we have of our electrical lead set is going to give us a lot of artifact or a lot of bouncing of that line instead of the clean shapes that we see here. And if you'll recall, we have a nice waveform here with a P, a Q, R, S, and a T complex. So our data looks good. This is our example data, and this is the data from our participant. We'll click continue. So in this case, we would have our participant complete a supine or lying down test. We'll go ahead and skip that, and we'll just do our seated test. And so now from our seated test, we'll click record here. We'll have the participant remain nice and still. And we'll collect a good 20 seconds of data. And you'll see here that during this 20-second collection of data, as I was talking here at the very beginning, there was a slight elevation of the heart rate. And as I relaxed, you can see the heart rate started to level off. And that's why we collected for a full 20 seconds, because we've really got a leveling off of our heart rate here in this range. So that's what we would expect to see. And that's the data right here that we're going to analyze as we start to see this flat part of the curve. And that flat part of the curve of the example data is very clean. And we got an example of our data here looking pretty clean as well. So we've got some good data there. We'll go ahead and click continue. Now for this next test, we're going to do a deep breathing exercise where the participant is going to inhale deeply and exhale deeply. And during each of the inhales and the exhales, we'll press the F4 and the F5 button to indicate when the inhale began and when the exhale began. So with that, let's proceed. We'll get some resting values here, some resting data, kind of let that heart rate stabilize. We have some stabilizing of the heart rate, so we'll go ahead and do our inhales and exhales. Breath in. Okay, we'll go ahead and click suspend there. And so what we can't see from the computer screen here, but on our example data and here up above, we have some arrows that show up. And those arrows indicate when we had an inhale and when we had an exhale. And so we've got some good data here. We'll go ahead and continue as we proceed there. Now the final task that you would have is to complete 2 minutes of exercise, something that's going to elevate your heart rate. Standing squats, jumping jacks, mountain climbers, get an elevation of heart rate. And from there, when you hit the record button after you sit back down and you're reconnected to the lead set, and we'll analyze your exercise or post-exercise heart rate. So from there, we'll go ahead and pause the video, but that will be our final task, is to complete our 2 minutes of exercise, sit down, have the participant connected, and then look at what our change in heart rate is.
Okay, let's take a look at some sample data. So we'll open up our BSL software and we'll look at lesson 5. Do make sure you look to see which person's data you're going to analyze. I'll go ahead and open up here Gale lesson 5 as an example. Okay, so once you have the Biopac BSL software loaded, you'll have your data that shows up on the screen. There are a couple of tasks that you need to complete today. Looking at our background document, this gives you a little bit of information to read. One of the areas of interest is going to be this figure right here, because this is going to tell you, again as a reminder, which of these segments are needed when you complete your data analysis. Now your procedures here highlight everything that you need to do, how the participant would be set up, the data that would be collected, the positioning, and down here at the bottom we have our data analysis. So I encourage you to take a look at the data analysis document so that you can determine how to go about analyzing this data. Now from this perspective, we have our data sheet. This is everything that you're going to record for this lab. We're going to record data from cardiac cycles, 3 different ones: supine, seated, start of inhale, exhale, and post-exercise. We're also going to be looking at ventricular systole and diastole, as well as different components of the EKG, and that's what I mentioned a moment ago was going to be quite helpful when you went to analyze the ECG components, looking at that background document. So you'll complete the tables for our resting values. This is from our supine recording, and this will be from our post-exercise recording. Okay, let's go back to our Biopac data. Now, let me point you to all of the components of what we're looking at. This dot that's clicked indicates that all of this data right here is supine data. If I click on this dot right here, this tells me that all of this data is seated data. If I click on this dot here, this tells me that all of this data is our deep breathing data. And if I click on this dot here, this would be everything post-exercise. Now I want you to take note of how the Biopac functions. Please be aware that it takes a couple of seconds after a recording begins for the Biopac to start analyzing and recording the beats per minute. So if I was to look at these first couple complexes, you'll notice that the Biopac hasn't started to pick up heart rate yet. That means when I go to do my analysis, let's say of my supine data, I'm going to want to zoom in on this middle set of data, because if I use this first part, I'm going to get some incorrect or erroneous values. So it's from here that I would use the first complex after the heart rate starts to pick up, that I would move from my R wave to my R wave. This would be my first cardiac cycle. And then if I look at my 40 value, this would be the first value that I would plug in on my data sheet. So going back to our Biopac data sheet, do you see here is our supine data, cardiac cycle 1. If we were using Gale, this would be our first cardiac cycle. This would be the first data that we would record, 40 value, 55.97. And that's what we see here, 40 value, we would write that value right down there. You'd go through the seated, the start of inhale, the start of exhale, and the post-exercise, complete your cardiac cycle 1, 2, and 3. Onto your ventricular systole and diastole. Again, take a look at that background document that's posted for you. That's going to assist you with determining what corresponds to ventricular systole and ventricular diastole. We'll go back and take a quick peek. So if we look at ventricular systole, that would be right here. It would go from the R wave to 2/3 of the T wave. This would all be ventricular systole. So on your recording, you'd record from the R wave to 2/3 of the T wave. Now ventricular diastole, this would go from the back third of the T wave to the next R wave. This would be ventricular diastole. So as you're asked to record your values here for 1 delta, you're going to look at ventricular systole and diastole for both seated and post-exercise. Your ECG components, again, looking at the P, the QRST complex. That's also going to be in the procedure data analysis document, but also in this document here, telling you where your P wave is, your PR segment, your QRS complex from here to here. So this gives you an indication of how those values would be recorded. So this should be everything that you need to complete your data analysis on and data recording on the tables, and then you have a series of discussion questions which you'll answer on the back side of this data sheet. Good luck, everybody.